Across the interstellar medium, large amounts of gas and dust clump together to form stellar nebulas. These nebulas, made mostly of hydrogen and helium, slowly change over time due to the effects of gravity, which pulls the particles in a nebula together. After a large clump reaches a critical density, it'll collapse and form the beginning of a star's core, also known as the protostar. This protostar sucks in the materials around it through a process known as accretion. As the protostar condenses and continues to suck in materials, it will increase in pressure and thereby increase the temperature. When the protostar reaches around 10 million Kelvin, nuclear fusion begins. The start of nuclear fusion marks the star's entrance into the main sequence, where it will spend around 90% of its life. Nuclear fusion occurs when two hydrogen nuclei collide. This process requires an incredibly high temperature due to the fact that it needs to overcome the repulsive electrostatic force caused by the protons of two hydrogen atoms. We know from Coulomb's law that like charges repel, meaning that the two protons in the hydrogen atoms will repel each other at great magnitudes when close together. Thus, to overcome this electromagnetic force, the hydrogen atoms need a large amount of kinetic energy. This large amount of kinetic energy can be gained with an increase in temperature. Higher temperatures cause particles to vibrate faster and obtain higher speeds. Kinetic energy is proportional to velocity squared, meaning that a small increase in a particle's speed can create a massive amount of kinetic energy. When the two hydrogen nuclei are finally able to overcome the repulsive forces and collide, they produce a helium atom, a neutron, and most importantly, large amounts of energy. The energy generated from nuclear fusion bursts outwards from the core of the star towards its surface. This large nuclear force is counterbalanced by the inward effect of gravity going towards the star's core. The star finds a Goldilocks zone where the two forces cancel each other out, known as hydrostatic equilibrium. During this period of equilibrium, the star's characteristics are determined by its mass. For example, the larger a star's mass, the faster it will use its fuel and exit the main sequence. Additionally, the luminosity of a star is correlated to the mass given by this proportionality, first noted by South African astronomer Jacob Holm. With a star's temperature and luminosity, we can graph it on the HR diagram, which is used to classify stars. We can also derive a star's lifetime on the main sequence by combining the mass-luminosity relation with the nuclear timescale equation to get this equation, where its lifetime on the main sequence is inversely proportional to its mass cubed. Now you might be wondering, Jack, how do we even measure the mass of those giant fiery balls in the first place? Well, that's a great question. Astronomers can find the mass of stars by studying binary star systems, where two stars orbit a center of mass. By observing their motion and using Kepler's equations, astronomers are able to find the mass of stars even light years away. Stars spend the majority of their lifetimes in the main sequence stage, where hydrogen fusion occurs in their cores. When the hydrogen at the center is depleted, the star begins fusing hydrogen in surrounding layers, causing it to expand dramatically. Its radius can increase up to 400 times its original size. As it grows larger, its surface cools, giving it a reddish glow, and it becomes a red giant. Red giants are significantly larger than the sun, up to 100 times its size, but have only 0.25 to 8 times its mass. Their surface temperatures are cooler, typically below 4,000 to 5,000 degrees Kelvin. As the outer layers expand, the core contracts under gravity, becoming hotter and dense enough to ignite helium fusion. This process causes the star to shrink, heat up, and emit a bluish glow. However, this helium burning phase is relatively brief, lasting only about 1,000,000 years. After the helium supply in the core is exhausted, the core contracts again, while helium fusion occurs in the outer layer. The star's outer layers expand and cool once more as it enters a second red giant phase. In this phase, red giants can engulf nearby planets. In about 5 billion years, our sun will reach this stage and is expected to consume the inner planets, including Earth. Fortunately, this is a distant future event. After the red giant phase, stars will split off onto two pathways. One for small mass stars between 0.8 and 8 solar masses, and one for large mass stars between 8 and 150 solar masses. One of the final stages of a small mass star is the ejection of the star's outer layers, forming a planetary nebula. This glowing shell of ionized gas is illuminated by the exposed core of the star and often displays intricate and colorful patterns. The planetary nebula phase is short-lived, lasting tens of thousands of years before the gas disperses into space. What remains after the planetary nebula dissipates is the star's core, now a white dwarf. White dwarfs are incredibly dense objects composed primarily of carbon and oxygen. With no ongoing fusion, the white dwarf glows faintly due to residual heat. Over billions of years, it will gradually cool and fade, eventually becoming a theoretical black dwarf, a cold, inert remnant. However, the universe is not old enough for any black dwarfs to exist yet, so they are still theoretical. White dwarfs represent the final stage for all low-mass stars. They are roughly the size of Earth, but contain a mass comparable to the Sun. High-mass stars have vastly different evolutionary paths compared to their low-mass counterparts, primarily due to their immense mass and higher core temperatures. The collapse of a red supergiant creates an immense shockwave that propagates outwards, resulting in a core collapse supernova, one of the most powerful explosions in the universe. The energy released in the supernova is so intense that it creates elements heavier than iron, such as gold and uranium, through a process called rapid neutron capture. These newly formed elements are ejected into space, contributing to the formation of future stars and planets. The fate of the core of the star depends on the mass of the original star. If the remaining core is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star. These incredibly dense objects are composed almost entirely of neutrons, with a mass comparable to the Sun compressed into a sphere only about 10 kilometers in diameter. Neutron stars often exhibit extreme magnetic fields and rapid rotation, emitting beams of radiation as pulsars. If the core's mass exceeds approximately 3 solar masses, the collapse continues, forming what is known as a black hole. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape it.
In nebulae where whispers glow, a star is born, its heart aglow. Through fusion's fire it shines so bright, a beacon in the endless night. It swells and shifts, a giant's flame, then fades. No two stars end the same. A nova's burst, a black hole's pull. The cycle turns, forever full. From death, new stars again will rise. Eternal life within the skies.